When the output of a model is affected by more than one phenomenon, meaning more than one transfer function, or more than one input, the respective transfer functions can be either added or multiplied. When the effects of two phenomena are added, they're represented by parallel paths in a block diagram, like the one shown here. However, when two phenomena are multiplied by each other, their respective transfer functions are represented in series in block diagrams. Let's consider two surge tanks positioned in series. The effluent flow rate from each tank is proportional to the liquid level. So the flow rate Q1 is 1 over R1, a resistance, multiplied by the tank level H1. And the effluent Q2 is 1 over R2, where R2 represents a resistance, multiplied by H2. Now we can ask a question, how is a change in Qi, the inlet flow rate to the first tank, propagated to Q2, the flow rate coming out of the second tank, assuming constant density for the fluid in the tanks? We can use total mass balances, and since we're assuming constant density, these can be simplified to volume balances. The volume of fluid in each tank is given by a cross-sectional area multiplied by the tank level, or H. So the accumulation of fluid in tank 1 is equal to Qi minus Q1, where Q1 is directly proportional to the height of the fluid in the tank H1. And the accumulation in tank 2 is given by Q1 minus Q2, where Q1 and Q2 are both replaced by the functions of the tank levels H1 and H2 respectively. We can define deviation variables, subtract the steady state equations from the dynamic equations, and take the Laplace transforms of all four of these equations. From these Laplace domain algebraic expressions, we can define several transfer functions. We'll call G1 of S the transfer function relating changes in Qi to changes in the height of the first tank. And we'll call G2 of S the transfer function relating changes of the height in the first tank to changes of the height in the second tank. Finally, we'll call G3 of S the transfer function relating changes of the height in the second tank to changes in the effluent flow rate Q2. The transfer function G1 of S is obtained by solving the first dynamic equation. The transfer function G2 of S is obtained by solving the second dynamic equation. And the transfer function G3 of S comes from this algebraic expression for the gravity-driven flow out of tank 2. Finally, to find how Q2 prime is affected by Qi prime, we simply need to multiply these three transfer functions together. Multiplying them will allow us to cancel H1 prime in the numerator and denominator of G1 and G2, and cancel H2 prime in the numerator and denominator of G2 and G3. And that will give us Q2 prime over Qi prime, or the product G1 of S times G2 of S times G3, which is just a constant and is not a function of S. This gives us a transfer function that's easily written in the gain and time constants form. What is the steady state gain of this transfer function? Does this steady state gain make sense on physical grounds? That is, if you increase Qi by a constant amount, would you expect Q2 to increase by that same constant amount, or by some fraction of that amount, or some multiple of that amount at the new steady state? We can see from this transfer function that the time constants, tau1 and tau2, that will describe the dynamics of the approach to steady state are a1r1 and a2r2. What kinds of transfer functions are these? If you said that G1 of S and G2 of S are first-order transfer functions, then you're correct. And of course, Q2 prime over Qi prime is a second-order transfer function, because it has a second-order polynomial in S in the denominator. Now we've looked at three different types of transfer functions. In later chapters, we'll discuss some variations on these three different types of transfer functions. But for now, I want you to be able to recognize the phylogeny of these three different types of animals in our transfer function zoo. Integrators have functionality of 1 over s, whereas first-order transfer functions have a tau s plus 1 in the denominator, and second-order transfer functions can be written in either the gain and time constants form with tau1s plus 1 and tau2s plus 1 terms in the denominator, or they can be written in the polynomial form with second-order polynomials in s in the denominator. The gain and time constants form can be readily converted to the polynomial form by simply multiplying the two terms. The surge tank is an integrator, which means that the surge tank integrates the inputs and outputs. The mixing tank gave rise to first-order transfer functions, and we saw some first-order transfer functions in the gravity-driven flow out of each of these two tanks individually. When we had processes that occurred in series, such as Q heating the heating element, which then heated the fluid in the tank, or in parallel, where Ti entering affected T and it affected Te, then this gave rise to second-order transfer functions. These two processes are also two first-order transfer functions in series that give rise to a second-order transfer function. All of these transfer functions were derived from linear models, that is, they came from linear sets of ODEs. It's not unusual, of course, when modeling chemical and biological processes to encounter nonlinear ODEs. In the next video, we'll review how we can linearize ODEs so that we can take their Laplace transforms and derive transfer functions even for nonlinear systems.